Right. So, very good afternoon to you all. I welcome you all for today's EMF session. In my last class, I have discussed um, three small topics: continuity equation. So, continuity equation is also called as a continuity of current, right? The current leaving a surface is equal to the current decreased within the surface. So that is continuity equation. In other words, the del dot J is equal to minus dou rho V by dou T. Del dot J in the sense divergence of current density. That means current diverged, right? Current diverged from a closed surface is equal to a rate of decrease in charge density, and that is called the continuity equation. And we have seen current and current density later, the relationship between current and current density, and the expression for convection current, J is equal to rho V into V, right? So in this equation, V, small v is the velocity. It is not volume, it is velocity, right? So please make a note of it. And then we have discussed Poisson's and Laplace equation. So del square V, Poisson's and Laplace equations we have derived from Maxwell's first equation, that is del dot D is equal to rho V. So del square V is equal to minus rho V by epsilon naught. So this is Poisson's equation, and when a region is charge free, then rho V is equal to 0, and then we have del square V is equal to 0, which is called Laplace equation, right? So Poisson's and Laplace equation, and del square V can also be expressed in terms of different coordinate systems, Cartesian, cylindrical, and spherical coordinate systems. How to express that I have explained in my last class, right? So now today we are going to discuss one last topic in third unit, that is capacitance. So this is one more important topic which we are going to discuss today, right? Capacitance. So basically, what is capacitance? What is the definition of capacitance? We know that C is equal to Q by V, right? So this is the definition of capacitance, right? So that means the ratio of charge to the potential difference, right? The ratio of charge to the potential difference. So this is the basic definition of capacitance. C is equal to Q by V, Coulomb per volts, right? Coulomb per volts are the units for capacitance. In other words, farads, right? Farads. And if you look at this equation, C is equal to Q by V, here the ratio Q by V is constant. The ratio Q by V is constant. That means what? If Q increases, V decreases, right? If Q increases, V decreases, such that the ratio Q by V is constant. If Q decreases, V increases, right? So the ratio Q by V is always constant. So from this we can say that capacitance C does not depends on Q and V, right? Capacitance does not depend on what? Q and V, right? Q and V. So capacitance does not depend on charge Q and V because the ratio Q by V is constant. Then capacitance depends on what? How we can change the value of a capacitor. The value of capacitor depends on the physical dimensions of the capacitor, right? The physical dimensions of the capacitor and the dielectric material used, right? So therefore capacitance, it depends on physical dimensions, dielectric material used, and spacing between the plates, right? Spacing between the plates. So spacing between the plates in the sense what? As we know that capacitor is formed by separating two conducting plates separated by dielectric material. A capacitance is formed. A capacitor is formed, right? The value of capacitor is called as capacitance, right? The value of capacitor is called capacitance. So this is the basic definition of capacitor. And in this, we are going to discuss about different types of capacitors. Number one, parallel plate capacitor. And second one, cylindrical capacitor, and third one, spherical capacitor. So these are three different types of capacitors which we are going to determine the capacitance value using electrostatic concepts. Parallel plate capacitor, cylindrical capacitor, and spherical capacitor. Right. So let us see one by one, and let us try to determine the expression for capacitance. Right. So first one, let us consider parallel plate capacitor. Parallel plate capacitor. So parallel plate capacitor. So what is meant by parallel plate capacitor? The name itself will give you some idea. Parallel plate in the sense two surfaces or two conducting planes, right? Two conducting planes separated by distance is called as a parallel plate capacitor, right? So for example, let us consider so this is one conducting plate, and this is another conducting plate, and these two are parallel. And I'm considering these two parallel conducting plates on z-axis, right? So here, so this is z-axis, right? Or xy, and this is 0, right? So along z-axis I'm considering that means what? Let us say these two are separated by a distance d. These two conducting plates are separated by a distance d. So that means what? the lower plate is at D is equal to 0. Sorry. The lower plate is at Z is equal to 0, and the upper plate is at Z is equal to D. Right? So that means they are separated by a distance D. Right? And assume that the charge density on the lower plate is rho s, and the charge density on the upper plate is minus rho s. Right? The charge density on the surface of the lower plate is plus rho s, and the charge density on the surface of the upper plate is minus rho s. Right? So therefore, two conducting plates, two conducting plates parallel to each other are separated by a distance d, right? By distance d, uh, and are separated with dielectric material. Dielectric material is called parallel plate capacitor. Right? It's called parallel plate capacitor as shown in figure. Right? So our aim is to determine capacitance. By definition, what is capacitance? So by definition, capacitance is equal to C is equal to Q by V. Just now I have given the definition of capacitance. So C is equal to Q by V, where what is Q? Q is charge, and Q is equal to surface integral rho s ds. Right? Q is equal to surface integral rho s ds, because we are considering conducting plates, right? Conducting plates which are surface, right? So they are having surface, right? So and the charge on the surface is uniform, right? Charge on the surface is uniform, so therefore rho s can be taken outside, and surface integral ds. So surface integral ds is nothing but area, right? Surface integral ds is nothing but area, right? So this is area. This one, surface integral, is nothing but area. And let us say that area of the plates is a, right? Area of the plates is a. So a is the area of the plates, right? So then we can write here rho s into a, right? Rho s into a, straight away we can write a, right? Because a is the area of the plates, and where a is equal to surface integral ds, right? So therefore rho s into a, and let us say this is equation 2, right? Rho s into a, q is equal to rho s into a, and this is equation 2. Similarly, v, what is v? V is equal to minus integral E dot dl, initial value to final value. So this is expression for potential, right? So earlier we have discussed this one, right? So here to determine potential, we require electric field. Let us say this is equation 3. Let us keep aside. And in order to determine potential, we need to determine electric field, right? So let us try to determine electric field due to a parallel plate capacitor, right? Electric field due to a parallel plate capacitor, right? So earlier, electric field due to a surface we have determined, right? Electric field due to a surface we have determined, and here we use that expression, electric field due to a surface. So what is the expression for electric field due to a surface? E electric field due to surface charge is given by E bar is equal to rho s by 2 epsilon naught a n bar, right? So this is the expression for electric field due to a surface charge, right? So this we know. And now in order to determine electric field due to parallel plate capacitor, we use this expression, right? So now rho s is known, right? So on the lower plate, rho s is plus rho s, and on the upper plate, rho s is minus rho s. Only thing is we need to determine the normal unit vector a n bar, right? To determine normal unit vector, we need to know the point P. That means the point where electric field is going to be determined, right? So at what point we need to determine electric field? There are different possibilities we have, right? So when possibility 1, when z less than 0, that is one possibility. When z greater than d, that is the second possibility. And when z is in between 0 and d, right? When z less than 0, and when z greater than d, and when z is in between 0 and d. These are the three possibilities which we can determine the electric field, right? So if z is less than 0, if z is less than 0, let us consider this possibility, right? If z is less than 0 means what? The point is somewhere here, right? The point is somewhere here. Here is the point, right? Here is the point, right? So if this is the point, what is the electric field? The total electric field is electric field due to lower plate and electric field due to upper plate, right? So because we have two surfaces here, right? Two surfaces we have, right? Lower plate and upper plate. So therefore the total electric field at z less than 0 is the electric field due to lower plate and electric field due to upper plate, right? So therefore here electric field due to lower plate, let us say this is E plus, right? Electric field due to lower plate is E plus, because the charge density is plus rho s. This is equal to rho s by 2 epsilon naught a n bar. What is a n bar here? What is a n bar? A n bar is minus az bar, right? A n bar is minus az bar, right? So because we know that the field directs towards the point, right? Electric field directs towards the point. So towards the point in the sense what? With respect to lower plate, I'm talking with respect to lower plate. So therefore electric field directs towards the point like this. So towards the point in the sense what? Towards negative z axis, right? Towards negative z axis, right? So therefore minus az bar. Similarly, electric field due to upper plate is E minus, right? Electric field due to upper plate is E minus. E minus is equal to minus rho s by 2 epsilon naught. Minus rho s here. Why minus rho s? Because the charge density on the surface of the upper plate is minus rho s, right? So therefore minus rho s by 2 epsilon naught into a n bar. Now what is a n bar here? With respect to the upper plate, what is a n bar? So even with respect to upper plate also, the electric field directs towards the point, right? Electric field directs towards the point. So towards the point in the sense what? Towards negative z axis. So therefore minus az bar, right? Minus az bar. So therefore the total electric field E is equal to E minus plus E plus, and this is equal to 0, right? So this is equal to 0. So therefore the electric field at z less than 0, right? The electric field at z less than 0 is 0, right? Is 0. Z less than 0 in the sense what? Outside the capacitance, right? Z less than 0 and z greater than d, and these two cases are outside the capacitor. So therefore outside the capacitor the electric field is 0, right? And let us also consider z greater than d also, right? So let us find out what will happen. So let us consider the second case. If z greater than d, right? Z greater than d, right? So z greater than d, z greater than d in the sense what? Somewhere here, right? The point is somewhere here. Let us say the point is here, z greater than, right? So let us say this is the point, right? When z greater than d, this is the point, right? So when this is the point, then the electric field with respect to lower plate is towards the point, and similarly the electric field directs towards the point with respect to upper plate, right? So with respect to lower plate and with respect to upper plate, the electric field directs towards the point. Towards the point in the sense what? Plus az bar, right? With respect to lower plate, an bar is plus az bar, and towards the upper plate is also plus az bar, right? So now electric field due to lower plate is E plus is equal to rho s by 2 epsilon naught az bar, right? Plus az bar, and similarly E minus upper plate is equal to minus rho s by 2 epsilon naught, and this is also az bar, right? Now what is the total electric field? E is equal to E minus plus E plus, which is equal to 0, right? Which is equal to 0. So therefore from these two cases, right, from these two cases we can conclude that, right, from this case and from this case, right? So from these two cases we can conclude that the electric field outside the capacitor is 0, right? Electric field outside the capacitor is 0, right? So you cannot sense electric field outside the capacitor. So therefore electric field exists where? Electric field exists inside the capacitor, right? Electric field exists inside the capacitor. So therefore now let us take the third possibility. So what is that? And the third possibility is at z in between right? Z in between 0 and D, right? Z in between 0 and D, that is the third possibility, right? So Z in between 0 and D, in the sense the point is between, right? The point is between the two plates, right? So that means somewhere here in between. So this is the point now in third case, right? So in between, this is the point now. So therefore, with respect to lower plate, what is the direction of electric field? Towards the point. And similarly, with respect to upper plate, what is the direction of electric field? Towards the point, right? So therefore, with respect to lower plate, towards the point, in the sense towards positive z axis. With respect to upper plate, towards the point, in the sense towards negative z axis, right? So therefore, with respect to lower plate, it is plus az bar, and with respect to upper plate, it is minus az bar, right? Towards the lower plate, it is plus az bar, and towards the upper, with respect to upper plate, the electric field direction is minus az bar, right? Is minus az bar, right? So therefore, right? So therefore here, electric field, right? Electric field with respect to lower plate is E plus, which is equal to rho s by 2 epsilon naught az bar, and with respect to upper plate, E minus is equal to minus rho s by 2 epsilon minus az bar, right? So just now I have discussed, right? With respect to lower plate, it is plus az bar. With respect to upper plate, it is minus az bar, right? So therefore here, this what will get, minus and minus will get cancelled, and we have plus az bar, right? So therefore, with respect to upper plate and with respect to lower plate, the electric field is same. So therefore, the total electric field E is equal to E minus plus E plus is equal to rho s by epsilon naught az bar. Let us say this is equation 4, right? So therefore, at 0 less than z less than d, the electric field is non-zero, right? Electric field is non-zero, right? It means what? Electric field exists within the capacitor or inside the capacitor. Electric field outside the capacitor is zero, not only for parallel plate capacitor, for everything, right? So inside is zero, sorry, outside is zero. Outside the capacitor, the capacitance, the electric field is zero, right? So therefore, equation 4 will gives you the electric field, right? So this is the electric field due to parallel plate capacitor, right? So once we know electric field, we can determine potential, right, from equation 3, right? So from equation 3, capacitor, just a minute, right? So from equation 3, and 4, potential V is equal to minus integral E dot dl. E, electric field. What is electric field? Rho s epsilon naught az bar dot dl. What is dl? dl is dz az bar, right? dl is equal to dz az bar. Why? Because the parallel plate capacitor is considered along z axis, right? Z is equal to 0 is one plate, and at z is equal to d, we have considered another plate, right? And now what are the limits here? Limits are d to 0, right? D to 0, right? That means initial value and final value. Initial value is the greater value. You just remember this one, right? So usually lower limit is less and upper limit is more, right? But whereas here lower limit is larger value, D and 0. That's because earlier while determining energy density, we have seen that the charges are moved from infinite distance, right? From infinite distance to the region where electric field exists, right? So we are moving from infinite distance is the initial value. So therefore infinite in the sense larger value, therefore initial value is D and final value is 0, right? So therefore V is equal to minus integral D to 0 rho s by epsilon naught dz. Then because az bar dot az bar is 1, right? Az bar dot az bar is 1, we will get this one, right? So simplifying this, we will get simplifying and substitute the limits, we will get rho s d by epsilon naught, right? Rho s d by epsilon naught, right? So therefore potential V is equal to rho s d by epsilon naught. So this is the expression for potential difference between the capacitor terminals, right? Between the capacitor terminals, right? So we have two capacitor terminals, right? So two capacitor, this is one terminal here we have, right? And this is another terminal we have, right? So the potential difference between these two terminals is the potential V, right? So in laboratory also we have seen capacitors, right? So 0.1 microfarads, 0.01 microfarads and 0.001 microfarads, all those capacitors you have come across, right? So now we have, right? So we have charge and we have potential, right? So therefore from equation 1, so what is equation 1? C is equal to Q by V. What is Q? Rho s into A, right? Equation 2, rho s into A. And V, what is V? V is rho s d by epsilon naught, right? Rho s d by epsilon naught, right? So if you simplify this, what will get? Rho s and rho s will get cancelled, and epsilon naught A by D, right? Epsilon naught A by D. So therefore C is equal to epsilon naught A by D. So this is the final expression for capacitance of a parallel plate capacitor, right? So this is the capacitance of a parallel plate capacitor, right? So from this we can say that capacitance of a capacitor depends on epsilon naught. What is epsilon naught? Epsilon naught is the dielectric constant, right? Epsilon naught in the sense free space. If the media between the two plates is air, then it is epsilon naught, right? Then it is epsilon. In general, it is not air; it is a dielectric material. So therefore, this is not epsilon naught; it is epsilon, right? So better to write epsilon A by D, right? Epsilon A by D, right? Because the medium is dielectric, right? So it is not air. If it is air, epsilon naught, right? So therefore, C is equal to epsilon A by D, and where epsilon is dielectric constant, epsilon is dielectric constant, A is area of the plates, and D is separation, right? Separation by which the two parallel plates are separated. That is the distance by which the two parallel plates are separated. That is separation or distance, right? So this is about parallel plate capacitor, right? And now let us move on to another one, cylindrical capacitance. Cylindrical capacitor, right? Let us discuss about cylindrical capacitor, right? So cylindrical capacitor, cylindrical capacitor. So whatever the capacitor may be, uh, determining capacitance, the procedure is same procedure we will follow, right? So now what is cylindrical capacitor? So cylindrical capacitor in the sense again same, inner cylinder and outer cylinder, they are separated by a dielectric material, right? Inner cylinder and outer cylinder, they are separated by a dielectric material, and that is called as a parallel cylindrical capacitor, right? So let us say this is the inner cylinder, right? So this is the inner cylinder, and outer cylinder, right? So inner cylinder and outer cylinder, outer cylinder, and this one is inner cylinder, right? And they are separated by a dielectric material. As usually they are separated by a dielectric material, right? So this is, they are separated by a dielectric material. This is all dielectric material, they are separated, right? And the radius of the inner cylinder, the radius of the inner cylinder is A, and the radius of the outer cylinder is B, right? The radius of the outer cylinder is B, right? Where B greater than A, right? B greater than A, right? And one more thing, the length of the cylinder is say L. The length of the cylinder is say L. L is the length of the cylinder, right? So therefore, capacitance again same procedure is nowhere differ. C is equal to Q by V, and let us say this is equation 1, right? Where Q is Q enclosed, right? So here, let us listen. So here to determine, okay, V is equal to minus integral E bar dot dl, right? So this is initial value and this is final value, right? And let us say this is equation 2 and this is equation 3, right? So here V is equal to minus integral E dot dl. So electric field is determined using Gauss law, right? Electric field is determined using Gauss law, right? So we know electric field due to point charge, we know electric field due to line charge, we know electric field due to surface charge, right? Surface charge, but we don't know electric field due to a cylindrical cylindrical like surface that we don't know, right? Parallel plate capacitor, we are using surfaces. So therefore, directly we have used surface electric field due to surface, but whereas here we need to determine, right? So therefore, to determine, I'm going to use Gauss law, right? To determine electric field, right? So to determine electric field using Gauss law, right? What is the procedure? Assuming Gaussian surface, right? Assuming Gaussian surface. So what is meant by Gaussian surface? What is meant by Gaussian surface? Gaussian surface means an imaginary surface, right? Gaussian surface is an imaginary surface, right? So therefore, let us imagine a Gaussian cylindrical surface, right? Gaussian cylindrical surface. Where we have to assume, where we have to imagine Gaussian cylindrical surface inside, right? Inside in the sense between inner cylinder and outer cylinder. That's because earlier we have seen that outside the capacitor electric field is zero, right? Outside the capacitor the electric field is zero, and even inside the inner cylinder is zero, right? The electric field inside the inner cylinder is zero, right? So electric field exists between inner cylinder and outer cylinder. Therefore, we have to assume Gaussian surface, Gaussian cylindrical surface in between inner cylinder and outer cylinder, right? So therefore, in between inner cylinder and outer cylinder, right? So let us assume, right, a Gaussian cylindrical surface like this. Right, so this is the Gaussian cylindrical surface, right? Gaussian cylindrical surface, right? And let us say the radius of the Gaussian cylindrical surface is r, and the length of the Gaussian cylinder is x, right? Is x, right? The length of the Gaussian cylinder is x, right? And now let us say the charge on the surface of the inner cylinder is plus q, and the charge on the surface of the outer cylinder is minus q, right? The charge on the surface of the inner cylinder is plus q, and the charge on the surface of the outer cylinder is minus q, right? So now let us try to determine electric field, right? So from this data, let us try to determine electric field, right? So to determine capacitance, we require Q and V, right? So from equation one, Q enclosed. So what is Q enclosed, right? What is Q enclosed? So here, for example, if the length of the cylinder is L, what is Q enclosed? If the length of the cylinder is L, Q enclosed is Q, right? Q enclosed is Q, right? So because the charge on the surface of the inner cylinder is Q, right? Charge on the surface of the inner cylinder is Q. So therefore, if length of the cylinder is L, charge is Q. If length of the cylinder is X, then what is Q enclosed? Then what is Q enclosed? So from this we can write what is Q enclosed here. From this, Q enclosed is equal to Qx by L, right? Cross multiply this into this is equal to this into this, right? So L into Q enclosed is equal to Q into X. So therefore, Q enclosed is equal to Qx by L, right? Qx by L. So therefore, Q enclosed is equal to Qx by L. And let us say this is equation 4. So this is the charge on the surface of the Gaussian surface, right? On the surface of the Gaussian surface is Qx by L. So therefore, we have Q, right? We have Q. And now potential. So to determine potential, we need to find out electric field, right? We need to find out electric field, right? So how we can determine electric field? To determine electric field, so we are using Gauss law, right? We are using Gauss law. So what Gauss law says? Psi here, I have forgotten to write this. Psi is equal to Q enclosed, right? So this is the Gauss law, right? So Q enclosed is this one. Q enclosed is this one, right? Then Psi, what is Psi? Psi is equal to surface integral d dot ds. So this expression we know, right? Xi is equal to surface integral d dot ds, and this is equal to charge on the surface of the cylindrical surface is uniform, so d can be taken outside. So surface integral ds. So what is surface integral ds? Surface integral ds is nothing but area of the Gaussian cylinder, right? Area of the Gaussian cylinder. So what is the area of the Gaussian cylinder? This is equal to d bar into, so what is the area of the Gaussian cylinder here? What is the periphery? 2 pi r, and length of the cylinder is x. So this is the area of the Gaussian cylinder, 2 pi r x, right? So r is the radius of the Gaussian cylinder and x is the length of the Gaussian cylinder. So therefore, area is 2 pi r x, right? 2 pi r x. So therefore, this is equation 5. So therefore, from Gauss law, right? From Gauss law, Q enclosed is equal to Xi, right? So that means equation 4 is equal to equation 5, right? Equation 4 is equal to equation 5 from Gauss law, right? So equating those two, what we will get? So equating those two, we will get d bar 2 pi r x is equal to qx by L, right? So x and x will get cancelled, and we have d bar is equal to q by 2 pi r L, right? A r bar, right? AR bar, right? So because electric field is a vector and AR bar, R is the radius of the Gaussian cylinder, so therefore unit vector is AR bar, right? Unit vector is AR bar. So the D bar is equal to Q by 2 pi RL into AR bar. And what is electric field? E bar is equal to Q by 2 pi epsilon R L AR bar, right? Since D bar is equal to epsilon E bar, right? D bar is equal to epsilon E bar. If it is free space, epsilon naught, right? So this is the expression for electric field, and let us say this is equation 6, right? And once we know electric field, we can determine potential, right? So once we know electric field, we can determine potential. So potential V is equal to minus integral E bar. E bar is Q by 4, Q by 2 pi epsilon R L AR bar, right? And DL. What is DL? DL is DR AR bar, right? Since DL is equal to DR AR bar, right? So that is the length, the radius of the Gaussian cylinder is R. Therefore, R component, we will consider R component. So DR AR bar. And what are the limits? Initial limit is B and final limit is A. So B is the radius of the outer cylinder, A is the radius of the inner cylinder, right? So 431, what are you doing here? Don't do silly things while class is going on. I will remember you. 431, right? So B is the radius of the outer cylinder and A is the radius of the inner cylinder, right? So we know that B greater than A, right? B greater than A. So larger value is the initial value and smaller value is the final value, right? So therefore lower limit is B and upper limit is A, right? So here AR bar dot AR bar is 1, and we have minus Q by 2 pi epsilon L integral B to A 1 by R dr, right? 1 by R dr, right? So integrating 1 by R. So integration of 1 by R, right? So do it, integration of 1 by R, and substitute the limits, you will get, right? So you will get potential. I will write down the potential expression for potential directly. You will get Q by 2 pi epsilon naught L Q by 2 pi epsilon naught epsilon L log B by A, right? So this you will get potential V, right? So after integrating and substitute the limits, right? Substitute the limits, you will get Q by 2 pi epsilon L log B by A, and this is equation 7, right? So therefore from equation 1, so from equation 1, C is equal to Q by V. So this is equal to Q by V. What is V? Q by 2 pi epsilon L log B by A, right? Log B by A. So Q and Q will get cancelled, and we'll get 2 pi epsilon L divided by log B by A, right? Log B by A, right? So therefore C is equal to 2 pi epsilon L divided by log B by A. So this is the expression for capacitance of a cylindrical capacitor, right? Capacitance of a cylindrical capacitor, right? So this is the procedure. So very simple, right? So let me go back and explain once again. So what is cylindrical capacitor? Inner cylinder and outer cylinder are separated by the electric material. It is called as a cylindrical capacitor, right? So capacitor, capacitance C is equal to Q by V, right? C is equal to Q by V. So therefore determine V, right? Determine V. So how to determine V? We know this expression, V is equal to minus integral E dot dl. So therefore if we want to determine potential, first of all we should know electric field, right? So therefore to determine electric field we apply Gauss law, right? So to apply Gauss law, assume a Gaussian cylinder in between inner cylinder and outer cylinder of length x, right? So Gauss law means psi is equal to Q enclosed. So Q enclosed is this, right? Q enclosed is this. Q enclosed, that means charge enclosed on the surface of the Gaussian cylinder, right? So Q enclosed is Qx by L, and similarly Xi, flux, electric flux. So electric flux crossing the Gaussian cylinder is this one, right? So from this expression we can determine electric flux crossing the Gaussian cylinder, right? And this is the area of the cylinder, and simplifying, right? So equating this is Xi, and this is Q enclosed, right, from Gauss law, right? And simplifying this, we'll get electric field. So this is electric field, and from this expression we'll get potential, right? Integrating, and Q by V, right? C is equal to Q by V. Substituting V value here from equation 7, substituting V value here, Q and Q will get cancelled, and we'll get the final expression, right? So this is how we can determine capacitance of a cylindrical capacitor, right? So therefore I have discussed two types of capacitors. One is parallel plate capacitor, and second one is cylindrical capacitor, and the capacitances of now you can leave the class. అయిపోయింది కరెంట్ పాయింట్ అబ్బాయి
ఏం చేస్తారండి మార్కెట్ చేస్తారా భయం అదే ల్యాబ్ మార్కెట్ చేస్తారా
మార్క్స్ కట్ చేసేయటం అసైన్మెంట్లు ఉంటాయండి. మా చేతిలో 30 మార్కులు ఉంటాయి, 30 మార్క్స్ లో కట్ చేసేస్తాం. భయపడుతున్నానండి. సాధారణంగా నా క్లాస్ లో కూడా చేయరు, అలా చేయదు. అది యానిటేషన్ పెన్ ఉంటది కదా, పెన్ తోటి గీసాడు స్క్రీన్ మీద. సెకండ్ ఇస్ వాళ్ళ ఫేసులు చూడలేదండి ఇప్పటివరకు. ఆఫ్లైన్ క్లాస్ లేవు.